Hi everyone, welcome to the Deep Learning course at the Technion Electrical and Computer Engineering Department, or ECE department in short. I'm Tal, and I'll be the instructor in this course. The tutorials will be accompanied with Jupyter notebooks filled with theoretical material and hands-on code examples in Python and PyTorch, the deep learning framework taught in this course. In the first two tutorials, we are going to recap and refresh some basic machine learning concepts that are important for deep learning as well. So let's begin. Okay. So in the first tutorial, we are going to cover some basic machine learning concepts that are important to understand where the course is positioned. And the first thing we are going to talk about is the different umbrellas of deep learning or machine learning in general. So the first thing we're going to discuss is supervised versus unsupervised learning. We roughly divide machine learning algorithms to 2.5 groups, and today we can even have more groups. Supervised learning means that along with our data, which are raw features, we are also given labels, which match labels or annotations, which match the features. For example, a dataset that contains images of cats and dogs, and each image is accompanied by a label, which is a dog or a cat, also termed the class. Typical tasks under this umbrella include classification, regression, and we're going to see even more tasks like object detection, segmentation, and things like that. Another umbrella is unsupervised learning. And in unsupervised learning, we are only given features from some data distribution, and we try to learn only from them without any known labels. So for example, a dataset that contains samples from a mixture of Gaussians, and we try to learn the parameters of the distribution, or discover patterns in unlabeled medical data using clustering. So typical tasks under this umbrella include pattern discovery, clustering, dimensionality reduction, and density estimation. Now the focus of this course is supervised learning. However, we are going to touch upon unsupervised learning or self-supervised learning a bit later in the course. Now the final subgroup is called semi-supervised learning. And in semi-supervised learning, we are given features, but also very few known labels. And it's usually the case that we can employ the standard supervised learning algorithm due to the risk of overfitting, a concept which we will discuss shortly in this tutorial. So an example for this kind of learning is a dataset that contains samples of regular data, and we are also given very few labels of anomalies in order to build a better outlier detector. This is also called an anomaly detection. I'll just note that there is another very dominant group in machine learning that is called reinforcement learning, but we will not address it in this course. So basically, the difference between supervised learning and semi-supervised learning is illustrated in this image. So we can see that in semi-supervised learning, we are not given labels for the entire data, but only for some of it. And we are going to try and learn from this little portion of labeled data that we have. And somehow, of course, we will need to utilize the unlabeled data to learn better. So this diagram pretty much summarizes the differences between supervised and unsupervised learning. And the focus of this course is going to be supervised learning, and we are going to talk about classification, regression, and all the tasks that are derived from this kind of tasks. And I'll also mention that we will use some dimensionality reduction techniques, which is an unsupervised learning task, but this is not the focus of this course. Okay. Now, an important concept in machine learning is that we want to learn some predictor, some classifier, regressor, or a model in general. And eventually, we are given some finite dataset, and we want to learn from this dataset a model that will hopefully generalize to unseen data. Now, this is in general called evaluation, or how we evaluate our models. And it's important to evaluate because eventually, if we want to deploy, or distribute our model, our classifier, or our machine learning model, then we need to determine how good it is on unseen data. So this is what we call generalization. And of course, there are many algorithms, and we want to be able to compare between different models, right? So we need some ways, some metric, some performance measure to compare between classifier. Now, ideally, the process will be to optimize the classifier to perform better on unseen data, and we need some way of doing that with what we have, because unseen data is unseen, so we don't have it. Usually, don't see it during training. So the way we are going to approach or allow evaluating our models is going to be some separation of our dataset. And the naive approach is to separate to train and test datasets. And I'll tell you in a bit why we call this the naive approach. And so this approach includes separating the data into train set and test set. That is taking a portion of the data of the for the training of the model. So, for example, 80% of the label data, and save another portion that on the side, which is going to be turned to a test set, which is usually about 20% of your data. And the model is not going to see this data during training. Okay, and we are going to use this set to evaluate our model, our generalization of our model. Now, keep in mind that these numbers, 80% and 20%, they depend on the number of data you have. So if you have a lot of data, then you can use this kind of portions. But if you have like very little data, then maybe 90% for train and 10% for test, that's also acceptable. Another thing that we do is shuffling the data. Now, it serves a couple of goals. So shuffling the data serves the purpose of reducing the variance and making sure that the model remains general and overfit less. So if we have some ordered data, we don't want our model to consider the order of the data when it is training, right? So we need to shuffle the data. Now, the popular case where shuffling is very important is when the data is sorted by their class or their target. Now, in this case, if we don't shuffle, then the model might consider the order of the data as important for the classification, and we don't want it. So by shuffling, we also add some randomness that assures that the training, test, and validation sets, so validation, I'll talk about it in a minute, are representative of the overall distribution of the data. So we are going to use some classic machine learning libraries like Scikit-learn, and a very known function in this library is called train test split, which makes our life easy when we want to split our data. So let's see how we can do this. So we are in this tutorial and the next one, we are going to work with a dataset called the breast cancer dataset. And this dataset is has about 500 samples, so this is not too many, right? And for deep learning, this is not a good dataset because we need a lot of data for deep learning. But for classic machine learning algorithm, this is enough. And this data is labeled with around 200 malignant samples, which are the positive, the good class, and the benign, which are sorry, it's the opposite. So the benign are the good ones, so it's the negative class. So we want to detect if the patient has cancer, and cancer is malignant, okay? So we also have around 300 benign samples, which are the negative class, which is the good, like you are healthy, right? Okay, so you can see a sample of data here. So we have around 500 examples with around 30 features for each example. We have the class, the label, right? And we also have different features, and most of them are continuous. And one thing I want you to notice is that the scale of the features are different. And this is going to become very crucial in later when we are going to train models, and we will need to rescale the data so every feature is on the same scale. Otherwise, if we don't scale the features, then the model might think that features with greater scale are more important for the classification. And this is generally not true. So the perimeter mean is usually not more important than smooth mean for classification, for the diagnosis classification, right? So we are going to bring the features to be of the same scale. And this is going to be important later. Right. So what we're going to do, we are going to build a regressor, or a classifier, in our case. So here in the first example, we are going to use the label diagnosis, and we're going to take two features, radius mean and texture mean, as our features for the prediction. So we are going to give our models the radius mean and texture mean, and from that it will have to predict whether the patient has cancer or they are healthy, right? So we have the train test split function, which is going to take the features and the labels, x and y. You are going to give it the portion of the data that you want to keep for the test set. And optionally, you can use stratification. So stratification means that you're going to maintain the same proportions of class labels in the train and test set. So for example, if you have 40% benign examples and 60% malignant examples in your data, then you want your train and test set to have the same portion. So you want to have 40% and 60% in the train set and 40% and 60% in the test set. So this is the process of stratification, and in order to stratify, you need to give this function the labels, so it knows what are the portions. Okay, so how do we measure, now that we have separated our data, how do we actually utilize the test? So what we're going to do, we are going to take some measurements or some metrics that are going to tell us whether whether our model is good or not. So usually we measure the accuracy or error estimate on the, and we usually do this both on the training data and on the test data. Now, when you use only the training data, this is not a good indicator of the performance on future data, because maybe the model has memorized the samples, and this is usually going to be called overfitting, right? And the classical curve which we are seeing in classic machine learning is that the accuracy or the error on the training set goes down, and the test set behaves differently. So at first it goes down, and then at some point it goes up. And this is an indication of overfitting. So we will discuss this a bit later. And the opposite of overfitting is underfitting, and it's usually at the beginning of training where the model is not fitted to the data at all. Okay. So why you usually see this? So test set going down and then going up. So the reason is that the new data that we get at test time will probably not be exactly the same as the training data. Our underlying assumption is that both the training data and test data are from the same distribution, but it's not usually the case, and there are some deviations. So this is why we need to keep some data on the side to understand our model performs on unseen data. So this is what a typical learning curve looks like, and later in the course in deep learning, we see a new phenomenon that is going to be called deep double descent, and in deep learning the curve looks a bit different, and we will talk about it later in the course. But keep in mind, this is relevant for the classic machine learning and also for deep learning, but in deep learning we are also seeing some new phenomena. Okay, so what we're going to do now is take it even farther. So the idea is that many models, they have something called hyperparameters, and these are parameters that are tuned or are chosen by the user, by the designer of the algorithm. And these parameters are not learned, they are not trained, they are selected before the training by the user, and they have great effect on the final performance, right? So an example of a hyperparameter is like the number of neighbors in the k-nearest neighbors algorithm, or the learning rate in stochastic gradient descent, which we are going to talk about in a few minutes, right? And you're going to choose an hyperparameter, you're going to train your model, test it, and see if you are happy or not. And if you're not happy, then you're going to change this hyperparameter and do the training again. Now, in this case, where we iterate over different hyperparameters, then separating to train and test is not a good idea. And the reason is that when you actually use the test set as your testing ground for new hyperparameters, then you actually leak data, because when you are actually tuning your hyperparameters to be good on this specific test set. And we don't want it, because this is not a good indication of what will happen on completely unseen data. and we want to prevent this data leakage. So this is why we are going to separate our data to a training set, a validation set, or on which we are going to tune the hyperparameters, and a test set which is completely unseen by the model and is going to be used as our final evaluation for the model. So another example for why it's unfair to use just a train and test set, then it is like taking an open material exam. So you're studying for an exam, but instead of bringing all of the material to the exam, you're actually bringing the material that is relevant to the question asked in the exam. And it's a sort of cheating, right? And we don't want it. So this is why we are going to have three subsets of the data set. We are going to have the train set on which the parameters of the model are learned, right? We're going to have a validation set on which we tune the hyperparameters, okay? The parameters that are not learned but are chosen by the user. And finally, we are going to have the test set, which is going to be completely untouched, right? And the model is never going to see this test set in any iteration. So not in the learning process, or not in the hyperparameter tuning process, right? So actually, the learning process is going to be like this. We are going to have some data set. We are going to choose some hyperparameters, train on the test set, train on the train set, evaluate our model with the chosen hyperparameters on the validation set. And if we are happy, then good. We can now test. We can take the final model and evaluate it on the test set. Otherwise, we are going to go back to the first step of choosing hyperparameters. We train the model, recheck the model on the validation set, and so on. Okay. Now the test set is just the final evaluation measure after you are satisfied with the hyperparameters of the model, right? Cool. And now, in this case, we need to consider how we separate the portions of each subset, right? So usually we do like 80% train set, 10% validation, and 10% test, and of course this depends on the number of samples that you have, right? So if you are on a very low data regime, then you can like take 5% for the test set and things like that. So keep that in mind. Okay. Another important concept which relates to what we talked about right now is cross-validation. Right? So separating to validation and test set is not very data efficient, as we now allocate less data for training, right? Because we now have three subsets. So cross-validation is a technique which is comprised of randomly splitting the data into k groups, and each k is going to be called a fold. Now, one of the groups is going to be used as the test set, and the rest are going to be used as the train set or the validation. So test or validation, right? The model is trained on the training set and scored on the test set, and the process is repeated until each unique group has been used as the test set. And this method is also called k-fold cross-validation. So you can see an illustration of this right here. So if, for example, if you want to separate to 5 folds, then we are going to have 5 iterations, and in each iteration, one of the folds is going to be used as the validation, and the other are going to be used as the train data. And this is good because this also gives us this also changes the actual samples in the validation set, and so we add more randomness and we have a better indication of the performance of the model. Now the final evaluation metrics are average over all the 5 folds, right? So this is a better indication. Now, let me just note that this is very good for the classic machine learning algorithm where training is faster and we don't need to think about the training time. Now, in deep learning, we are usually going to work with large models that are trained over a long period of time. So using k-cross validation is not the best of ideas. And in deep learning, we usually resort back to the standard train, validation, and test separation, right? So no cross-validation. But if you have a small model and small data and training of the deep learning model is fast, then you can, of course, do cross-validation. Now you can use the cross-val score in Scikit-learn for the classic machine learning algorithm. It works pretty good. Okay. Another important theoretical concept of the classic machine learning is the bias-variance trade-off, which is directly related to underfitting and overfitting. So let's discuss this a bit, and then I want to make sure that this concept is clear in terms of underfitting and overfitting, and then we can move on to the more practical stuff. So the bias-variance trade-off. This is an important result of statistic and classic machine learning, and it means that it helps us understand the model generalization error. And the idea is that the general error can be expressed as a sum of 3 different errors, and these 3 errors are called the bias, variance, and the irreducible error. So let's see how we can do this. So in this case, we are going to talk about regression task, okay? So let's say we have a true but unknown function f of x, so capital F, with noise f of x equals sum f plus epsilon, where f is a deterministic function and epsilon is a random noise, right? So usually a white noise. And we seek to estimate it based on n samples from a set D, which was collected from f of x capital F, right? So we have some noisy samples from a deterministic function. So we denote the regression function as g of x, and of course it's conditioned on D, right? The D is as input. And the error of the regression model is given by the mean squared error, which is an expectation over our data, and it's just a squared error over f of x minus g, our regressor, or the prediction. Okay, so minus g of x, right? So f is true, right? But we don't know it, we only have the values from the data. And we can actually take this mean squared error and decompose it to 3 terms. So you can see the full derivation on Wikipedia, but the derivation leads us to the following result. So this error can be decomposed to 3 errors. So we have the bias of the regressor of the model, right? Bias of g squared plus some sigma squared, which is not dependent on anything, plus the variance of the model of G, right? So the variance of G. So let's understand what each term means. So the first term is the bias. So the bias is the difference between the expected value and the true value, right? So remember that we have the deterministic function f, and this is the actual value without the added noise. And the difference between this and the expectation of the value of the model, this is the bias error. Now, this part of the generalization error is due to wrong assumptions. So, for example, assuming that the data is linear when it is actually quadratic. So, a high bias model is most likely to underfit the training data. So, basically, if we assume that the noise is, for example, some white noise, so in expectancy, we expect that that our model will be actually good. Okay. So if it's not, then something went wrong with our assumption or our model, and we need to think about it. The next type of error, and don't worry, I will try to illustrate this kind of error in illustration in a minute. The next error is the variance. So the variance, right, is this term here, and it's a bit complicated. So we can think about it as follows. So we have the expected value of the regressor minus g itself, okay, and the actual prediction, not the expected one, and we have it squared, and we take expectancy over that. So it's a bit complicated, but let's try to understand what this means. So this part is due to the model's sensitivity to small variation in the training data. So a model with many degrees of freedom, such a high degree polynomial model, so for example a very complex model, is likely to have high variance and thus tend to overfit the training data. And low variance means that the estimate of f does not change much as the training set varies. So I'll try to explain this in a minute, okay, the bias and variance. So what you need to remember about the variance is that it is directly related to the sensitivity of your model, right? So this illustration here tries to explain in a graph this error. So let's take a look. So if you have a very simple model, so you chose like a linear model to classify polynomial features, so the model is likely to have high variance or underfit, and the error will be large, right? However, when you increase the degrees of freedom of the model, the bias goes down. So and the training error, right, will go down. However, when we look at the variance, for example, so a very simple model is going to be less sensitive to the changing of the data. So it doesn't matter how many polynomials you will add. This linear model won't change much because it's linear, right? So it's going to be to have low variance. And this is also related to underfitting. When you increase the model, the complexity of the model, then the variance goes up because now the model becomes more sensitive to new data. So if you add another polynomial, then the model, when you refit it on the new data, it will change. So the regressor itself will change a lot. So it's very sensitive, right? And this means that the model is overfitted to your training data. And I'll show you another example in a minute. The final error that we have is called the irreducible error. It's denoted by sigma squared, and you can see here that it's not related and not dependent on the model at all, right? So G is not a part of this irreducible error. And by its name, you can understand that this part is due to the noisiness of the data itself. And the only way to reduce this part of the error is to clean up the data. So for example, fix the data sources, detect and remove outliers, and so on. Right, so this is why it's called an irreducible error, because it doesn't matter which model you choose, you can't reduce this error. Okay, so I'll just note again that this is the classical curve, and as we will see later in the course, there's actually something special that happens in deep learning, which is going to be called deep double descent, and it's different from what you see in this curve, but not by much. Okay, so let's jump to the board for a couple of minutes to understand the bias and variance a bit better. So here we are going to have a regressor, right? We want to regress this point. So this is our dataset. The blue points are our dataset. So the first thing I do is I pick a very simple regressor, like a linear regressor. So for example, our regressor will be something like this. Now we can see it's not very good, and for each point we have some error, and this error is going to be the bias. So this error here, the difference between the value and the expected value from the regressor is large, right? And basically this is what we're going to call a high bias model. And you can see here that it's very simple model. Okay. Now what else we can do? We can actually pick a more complex model, for example, like a polynomial. So we can have this kind of regressor. So we can see that now there is no difference between the prediction of the regressor and the actual data point. Now, this means that we have very low bias. However, this is usually considered overfitting. Now, let's understand why. So let's go back to the high bias example. So we have a linear model here, which tries to regress the points. However, what happens if we add a new data point here? So in green, right? How is the model going to change? Now we are going to retrain the model, okay, relearn the model, and the assumptions are the same. So we are going to have a simple model. So the red line, how is the red line is going to move when you add the new green point here? So the answer, it's not going to move much, because the reason the linear model is doing this is because on average, it wants to minimize the error. So it might move a bit up, but still not like it doesn't move much. So this is why it has low variance. So it's less sensitive when you add new data. So you added a new data, and the linear model did not change much. So basically, it's very not sensitive to the new data. So this means it doesn't move much, so there is low variance. However, let's take a look what happens when we add a new data point here. So when we add a new data point here, and we have a very complex model, right? Then, and we are not going to retrain the model, we are going to have a curve that looks like this. Now what you can see here is that the model changed a lot, right? Because of its complexity. So this means it has high variance. It's very, very sensitive. because when you added new data, the model changed a lot. So this is what we mean by high variance, right? The model is sensitive. So I hope it makes the bias and variance clear. So what you need to remember is that usually bias is related to the training error, how much in expectancy, of course, the model is wrong on the training data, and for the variance is how it is sensitive when we add new data. Okay, let's go back. So the next topic we're going to discuss is pre-processing and feature scaling. So this is going to be a fundamental part of the data pre-processing stage, and this is very, very relevant to deep learning as well. And this part makes or breaks your learning process, because if you don't scale your features, then you might get results or performance that are not satisfying, right? So what we need to do is we are going to take a look at our data and understand the scale of the range of the values of each feature, right? And if the ranges are very different, this means that we need to apply some normalization or scaling. So this kind of pre-processing in practice or empirically, it can improve the performance of some machine learning algorithm. It may break some others, but usually it helps, okay? And it is especially important for gradient descent-based algorithms such as linear regression, which we're going to talk about in this tutorial, logistic regression, and neural networks, which is the topic of this course. And it also affects some distance-based algorithms such as KNN, SVM, even PCA, and things like that. So we're going to talk about linear regression in more depth in a minute, but I want just to show you the update rule for linear regression. So you've seen it before. We are going to have a regressor age of theta that takes some features of m dimension and outputs some value, some scalar value, right? So this means that we are going to have m weights, m parameters for the regressor theta, and x's, the input features, are also of this same dimension. So the update rule, you can see it here. So for in each iteration of gradient descent, we're going to take some step alpha in the direction of the gradient, and the gradient in the case of MSC is calculated as follows. So we have the output of the regressor minus the ground truth value from the data, and it's multiplied by the feature. Okay, so by the jth feature. So the jth parameter is dependent on the value of the jth feature. Now what you can see here is that the presence of the feature value x in the formula will affect the effective step size of the gradient descent. So if the jth feature has a very large scale, then the effective step size will be larger, and the model or the learning process will tend towards the directions with the higher, with the larger scale, right? So basically, we induce that the features of larger scale are more important, and we need to go in their direction, and it's generally not true, right? So the difference in ranges of features will cause different step sizes for each feature. So to ensure that the gradient descent moves smoothly towards the minima and that the steps for the gradient descent are updated at the same rate for all the features, we scale the data before we feed it to the model. Now, having features on similar scale can usually help the gradient descent converge more quickly towards the minima. So what kind of scaling we can do? So the first one is called min-max scaling, and also usually referred to as normalization. So normalization is a scaling technique in which values are shifted and rescaled, so they end up ranging between 0 and 1, but you can choose different range like -1 and 1. It is also very popular. And the way we do this is we take the minimum value, and each feature we subtract the minimum value and we divide by the total range, which is xmax minus xmin. And you can choose these values, so you scale the data in your desired range. So it can be 0 and 1 for images, for example, or -1 and 1 for other kind of data. And it's very popular, right? And a thumb rule for using it, but empirically you need to use what works best. So normalization is good to use when you know that the distribution of your data does not follow a Gaussian distribution. And this can be useful in algorithms that do not assume any distribution of the data, like KNN and neural networks. So typically, for example, images which has pixel values, color values, though we usually normalize them between 0 and 1 or -1 and 1. We will see that later in the course. And we can also use standardization, which is the next normalization technique, but basically you use what works best. So for the classical machine learning algorithm, you can use the min-max scaler. So basically you take your training data, you learn the x-min you learn. You find the x-min and x-max, right? And you can also give it you can also initialize it with the desired range. So if you don't want 0 and 1, you need to tell your scaler what is the range of values. After you calculate the x-max and x-min, you transform your training data and you then transform the test data. Now, very important, when you learn or fit the parameters of the scaler, right, you only use the training data. Remember, we don't want to leak information from the training data to the test, from the test data to the training data. So if you were using the test set to fit the x-max and x-min, you're actually leaking data from the test set into your training data. We don't want it. So we keep them separated, and we only use the calculated parameters to transform the test set. We don't use the test set to learn the x-min and x-max. The next type of popular scaling technique is standardization. So it's a scaling technique where the values are centered around the mean with a unit standard deviation. So basically we want to empirically transform the data to look like it came from a unit Gaussian. Okay, so in theory, we justify this scaling technique from some statistical rules, but in this case, it empirically works really good. So CLT, if you're familiar with, but that's not important for this part. So it basically means that the mean of the features becomes 0 and the resultant distribution as a unit standard deviation. So instead of min and max, here we calculate mu and sigma. So mu is the empirical mean and sigma is the empirical standard deviation. And we calculate them again from the training data, right? So this can be helpful in cases where the data follows a Gaussian distribution. And however, this is usually not true, but it still works really good. Now, here is an interesting trait of standardization comparing to normalization. So unlike normalization, standardization does not have a bounding range. So even if you have outliers in your data, they will not be affected by standardization. So think about it. If you have some outlier, which is like its x-max is really large, then you actually squish your actual good values to an even smaller range. Right, because the outlier pushed the other values to some smaller range. Now, in standardization, we don't actually have a bounding number, right? So an outlier will remain an outlier. So this is important. Okay, so you can use this standard scaler from Scikit-learn, and again, we fit it on the train data. So we calculate mu and sigma on the train data, and then transform the train and test data, and the test data is not part of the fitting process. Okay, so what happens in practice? So at the end of the day, the choice of using normalization or standardization will depend on your problem and the machine learning algorithm that you are using. And you will use what works best. Okay, so we can always start by fitting your model to raw, normalized, and standardized data and compare the performance of the best results. Right? And it is good practice to fit the scaler on the training data, as I have mentioned, and then use it to transform the testing data. We don't want to leak information from the test data to the train data, and this is the good practice. Okay. Now, what about the labels? Should we scale them as well, especially in regression tasks? So the answer is that it is usually not required, but sometimes it does help. So keep in mind that is also something that you need to check. So if your target is a very large number, it might still affect the learning process. So keep in mind that you might need to scale the target values as well. Okay, so we will reiterate the normalization techniques later in the course, where we will discuss normalization inside neural networks, and we will see how standardization fits there as well. Okay, so let's talk about machine learning models. It's about time, right? So the first one is linear regression, and linear regression is basically fitting a linear model that makes a prediction by computing a weighted sum of the input features plus a constant called bias term, sometimes also called the intercept term. Okay? So keep in mind that here when we say linear, we mean linear by the parameters. So the parameters are linearly multiplied by the features. Okay, the features can be polynomials or whatever, but just the linear, it's just a linear combination, right? This is why it's called linear. So we denote y hat, the predicted value, and the number of features, xi the ith feature value, theta j is the jth model parameter. So the so theta j is goes according to is going to be multiplied by xj, right? And theta 0 is reserved for the bias weight, so you can think about it as like a constant feature, which is just the value 1, and it's multiplied by theta 0. So this is the bias. You can see it here. And in vector form, we can just have this vector multiplication, right? So just the dot product. And the output, as you can see here, it's scalar. It doesn't have to be a scalar. It depends on the output dimension, but in general, this is how it looks like. So we can look at linear regression problem as one application of single neuron, and we will discuss this in the next lesson. Right. So how do we train this model? So we need to talk about some loss function or cost function. So how do we train this model? So training the models means tuning its parameters, so the model best fits to the training data, right? So we want the output to be to match the ground truth value that we have in our data. Now, the most common performance measure on regression is the root mean square error, so RMSE, and thus we need to find a value of theta that minimizes the RMSE. Now, in practice, it's simpler to minimize the MSE, just the mean squared error without the root, because the same values that minimize the RMSE also minimize the MSE. So the MSE is as follows. So we normalize by the number of data samples that we have, and we just calculate the prediction of the regressor, right? So theta transpose x minus the ground truth value, and we take the squared error and take the average of it, so the mean, right? Now pay attention to the notation. So m is the number of samples and n is the number of feature, and this will change a lot in the course. So sometimes it's m, sometimes it's m, sometimes it's d. Just make sure you understand what letter is denoting what. Okay. Now, I want to give some motivation where this cost function comes from. So if you remember from the machine learning course, what we usually do is we actually care about the log likelihood. And when we assume that the likelihood is normal distributed like Gaussian, then we get the MSE. So let's take a little detour to understand where the MSE comes from. But basically, if you assume that the likelihood is non-Gaussian, for example, it can be a Laplace one, and in this case, the resulting cost function will be different. So it can be the L1 error, for example. Okay, so let's make a little detour and try to understand where this comes from. So we are going to assume that the true data comes from a deterministic function, right? So theta tx. And however, in the real world, we actually sample data, so some noise is added. So, and usually it's a white noise, which is zero mean Gaussian with some noise, with some variance sigma squared. Right? So we actually assume that the data is coming from a deterministic function, but because we take samples from the real world, then we have some added noise. Now, in this case, y is also a Gaussian random variable, right? It's a normal random variable where the mean is theta tx, the expectancy of this expression, and again the variance is just sigma squared. So this is just a scalar number. This is why the new random variable y is just as a mean of theta tx. So what we care about usually is the log likelihood. So we want to maximize the likelihood of the labels y given x, which is parameterized, and the model is parameterized by theta. Right? So we want to maximize the likelihood, but maximizing the likelihood is very similar to minimizing the negative likelihood. And in general, we also use the log likelihood because minimizing the or maximizing the log likelihood is the same as maximizing just the likelihood. However, using the log function is more numerically stable because the numbers are not very small. And it also turns each multiplication to a sum, which is simpler to calculate. So maximizing the log likelihood, MLE, is just minimizing the negative log likelihood, the NLL. So if we assume that this is a Gaussian, like we did here, and we calculate the log likelihood, then we get this term here. So we are going to maximize the likelihood or minimize the negative log likelihood. And when we open the terms here, we can see that we actually, so this part here is not dependent on theta, right? So we can, just the constant, we can ignore it. And then we also have this part, so the sigma squared is not dependent on theta, so we can just treat it as a scaling parameter, and we can just include it in the learning rate or whatever, right? It's just a scaling parameter. So basically, when you do this, you actually get that minimizing the negative log likelihood is just like minimizing the mean squared error. Very nice. But this all goes to our assumption, or go back to the assumption that we made that this is a Gaussian. If you assume other noises, so for example, in the next lesson, we're going to talk about Bernoulli distribution. And when you assume like a Bernoulli distribution, then the error becomes the binary cross entropy. Okay, so it is dependent on the choice of your choice of modeling of how you chose to model the likelihood. Okay, let's go back. So for this function, we actually have a closed form solution, right? So for this simple model, we can actually find the value of theta that minimizes the cost function, and there is a closed form solution, which means that we have a mathematical equation that gives the result directly. No need for an iterative optimization. It's also called the normal equation, and we will now derive it. So we want to find a solution y at equals x theta. This is our prediction for the value, right? And the parameters theta are obtained by minimizing the sum of squared error or residuals, right? So this is just this term. We can open the parentheses and get this term here. Now, when we want to minimize with respect to theta, we can just take the derivative and compare it to 0. And in this case, we get what's called the pseudo-inverse solution. So theta star, the optimal parameters are as follows. So we have xtx minus 1, so the inverse of this matrix, right? Multiplied by xt and y. So this is the optimal closed form solution, and this matrix is also called the pseudo-inverse of x, right? However, we won't always be able to do this. So take a look at the operations that are needed to calculate the optimal theta. So we have some matrix multiplication here, and also we need to take the inverse of it. So this is not a cheap operation, so it's quite expensive operation computationally, especially if you have a lot of features and a lot of samples. So think about deep learning, right? So you have like millions of examples. So taking the inverse of such a matrix can be very computationally expensive, or even not feasible at all. So what else can we do? So the general idea is to treat the parameters iteratively without the need to compute the inverse of any matrix. Okay, and the idea is to measure the local gradient of the error function with regards to the parameter vector theta or w, and it goes down in the direction of the descending gradient. Once the gradient is 0, the minimum is reached, and this means that we reach convergence. And the idea is that we are going to optimize the hyperparameter called the step size or the learning rate, right? And this is what we saw here and above. We call it alpha or eta sometimes. And this hyperparameter is important because if you pick it to be too small, then the algorithm will have to go through many iterations to converge, which will take a very long time. We don't want that. You can also pick it to be too high, and this might make the algorithm diverge as it may miss the minimum, right? So just oscillate here, and you will see the cost function fluctuate, right? We don't want it. We want to find the just right step size, and this is an art, right? Picking the right learning rate or finding the optimal learning rate, and we're going to discuss this later in the course, right? So how does it work? So here is the general recipe for the stochastic gradient algorithm, and it's also called mini-batch gradient descent, and let me tell you why. So what does this algorithm require? So we need to pick an hyperparameter. We need to initialize some weight parameters like the theta or w, right? And usually we can pick like a very simple initialization, like let's just initialize it with 0, but sometimes it's not a good idea, and we need to initialize it from some random distribution around 0. And we are going to go in iteration. So while stopping criterion not met, so stopping criterion can be like some epsilon change in the error, or some finite number of iterations, so maximal number of iterations. So we are going to take a sample of mini batch of m examples from the training set. So if your choice is m equals 1, then you're doing stochastic gradient descent. So you're taking a step over one example. This is very similar to the perceptron algorithm. And when you choose m to be the size of your data, then this is just gradient descent, right? So you take gradient over the entire data. However, the reason for using mini batches is that we are limited in terms of memory, and if you have a lot of data, then you need to work in batches. Otherwise, the data don't fit in the memory. So this is why we use a mini batch of size m. So what you're going to do is we're going to take this m with the corresponding, you're going to take these m samples with the corresponding labels ym, and compute the gradient. So you can see that the gradient is just the gradient here that we calculated for this term, for the mean squared error term. Now you can eliminate the 2, it's not important, you can just include it in the step size, right? And then you just take a step for the parameters in the direction of this gradient, and alpha k multiplied by g. And you continue until you cover the entire data space, right? And when we do this, so we are noting that there is a difference between an iteration and something we call an epoch. So a single epoch is considered when you covered the entire data once, right? And an iteration is just every update of the gradient. So here, this is just a single iteration. So every update of the parameters is an iteration. But at some point, you are taking mini batches, and at some point you cover the entire data. So when you cover the entire data, this is one epoch. And we're usually going to go over many epochs. So we are going to go over the entire data space multiple times. You can see the process right here. So we initialize our parameters somewhere. And hopefully, if the function is convex, then we are going to take some steps towards the closest local minima. If it's convex, then the local minima is also the global minima. Okay, so what we're going to do, we're going to take the breast cancer dataset from before, and we are doing a regression task. So in this time, we are trying to predict the perimeter mean from the radius mean and area mean. So just a regression task, right? We have a scalar output and 2 features as input. We are separating to train and test, so no validation for now. We are doing standardization, so in this case we're doing it in the raw form, like in NumPy, no need for Scikit-learn, right? And then we just are going to do stochastic gradient descent. So we are going to have a batch size of 16, and we're going to go over the entire data 10 times, so 10 epochs, right? And we are going to initialize our W, which is going to be two features, right? So we're going to initialize it with 0. Not the best idea, but it works for now. And then we are going to have the outer loop, which goes over the number of epochs, and the inner loop, which actually performs the gradient descent. And each iteration means a single gradient update. Okay, so we can see here that we just use the raw gradient that we calculated. And the @ sign is just matrix multiplication. And then we're going to take a step, and we're going to print the values of W. And note that our final solution, our final predictor and the predictor of the values is as follows. So we take the data and multiply it by W. So this is our prediction, very simple. You can see that it eventually converges around some values, right? And we can actually plot and see what we get. So what you see here is that in blue we have the ground truth value y, and in orange we have the prediction of our regressor, what we learned. So you can see here that the prediction is pretty good, especially in areas where there is a lot of data, and in areas where we don't have a lot of data, then the prediction is quite deviates, but that doesn't matter. So pretty good work, right? Now the final concept we are going to talk about is called regularization. And regularization is a technique to reduce overfitting. And basically this means that we are going to constrain the model, okay? So we don't want to give it complete freedom because this will quickly lead to overfitting, especially when you use very complex model. So the fewer degrees of freedom it has, the harder it will be to overfit the data. For example, in polynomial fitting, a simple regularization would be to reduce the number of polynomial degrees. So we're going to discuss two types of regularization, ridge and LASSO, but there is the general recipe for this case. And later in the course, we're going to talk about multiple regularization technique in deep learning, and we will see different types of regularization, and which are more interesting than just having a cost over the weights, which is ridge and LASSO. Okay. So ridge regression is a regularized version of linear regression where the regularization term is equal to lambda multiplied by the squared parameters. So basically, the larger the weights, the higher the cost. So the cost function will be larger. So basically, depending on the value of lambda, you're going to pay some cost for having large weights. And basically, this type of regularization will drive the weights to be zero. So it forces the algorithm to not only feed the data, but also keep the model weights as small as possible. And we only use it, of course, during training. So we don't care about it. Once we have the learned parameters, we don't care about the cost function at all. We just use it as our predictor. And the hyperparameter lambda, so we need to pick it as the designer. It controls how much you regularize the model. Now, it's very crucial, okay? So if you, so let's see what happens to the model according to the values of lambda. So when lambda goes to 0, we resort back to the unconstrained least square solution, right? So lambda equals 0, just the regular linear regression we know. Now, as lambda increases, then all the weights end up very close to 0, and the result is flatlined through the data's mean. So before we jump to the explanation, let's see what happens. So we have the blue data here, and we are trying to fit some predictor, so the orange one. And you can see what happens as we increase lambda. So as we increase lambda, we actually drive the model to be a flat line. So because in order to be able to be flexible, the model needs to have variable ranges of weights. But when you give a large cost for these weights, then it drives the weights to be 0. So this is why it is flat line. Okay, so now we actually can plug in the additional cost term, right? And we have actually the gradient is not that different, so just the added lambda theta. And we also can derive the closed form solution. So you can see that in the closed form solution, what's different is that we have this lambda identity here, which is added to the diagonal of xdx, and this is also ensures and make the calculation more stable, because now it assures us that we can actually invert the matrix, right? So you can see here, and we can actually use it from Scikit-learn, and you should tune the value of lambda, and here you can see the difference in weights. So now we have the first feature, which has the weight of 0.89, and the second feature, which has a value of 0.1. So this means that in order to predict or regress the value of the perimeter mean, then the first feature, which is the radius mean, is more important because it has gotten more weight, right? So you can see here that the actual result is not very different than the regular the unconstrained version, right? But still, again, you should tune the parameters, and of course measure the error and evaluate it on some validation set, and make sure that this hyperparameter is tuned correctly. Now, the second type of regression we're going to talk about is called LASSO. Now, LASSO is very much like ridge, but instead of L2 cost, we are going to use the L1 cost over the parameters, so just the absolute values. And the problem with that is the LASSO cost function is not differentiable at theta equals 0, so we don't have a closed form solution, but you can still use gradient descent. And in order to do this, we have something called subgradient. It's not important for now. Now, the difference between LASSO and ridge is that LASSO, it tends to eliminate the weights of the least important features, set them to 0. Basically, it effectively is doing something called feature selection and outputs a sparse model. So very few non-zero weights. Now, on the other hand, ridge regression will tend to shrink the large weights while hardly shrinking the smaller weights. So if you already have a small weight, it won't change it much. but if you have a large weight, then it will drive it to be smaller. And LASSO, the shrinkage will be directly proportional to the importance of the feature in the model, right? So if the second feature is not important, then it will drive it to 0. And we can actually see that when we apply LASSO here, and it's a very strong regularization, you can see that the second feature has a weight of 0. So basically we predict the perimeter mean based only the radius mean, okay? So you will see that the resulting model is a bit worse in performance. So you can see that we have a deviation from the ground truth value and the predicted values, but that's expected because LASSO is a stronger constraint, right? So it tends to output very sparse model, right? So in other words, with regression, we'll try to find a good model with small scale features as possible, while LASSO and regression will try to find a model with as few features as possible, right? So a sparse model, so feature selection. Empirically, we see that L1 regularization is much more robust to outliers, but you can use both. So this illustration tries to depict what happens when you use region and LASSO. So the orange area, the orange region, is the allowed values for the weight, for the parameters, and the blue one is just the objective function. You can see that the actual chosen parameters will be the intersection between the allowed region and the objective function. So you can see that in the case of ridge, we can have at the same point we can have values for both W1 and W2, but in the case of LASSO, it will drive the first one to be 0 and just pick the one for the second feature. Okay, now why not combine the both of them? So ElasticNet is a combination between region and LASSO, so you have two hyperparameters to optimize, and in general, you can take not the first one and second norm, you can actually take like the root square or even higher polynomials, right? So larger costs, and you can see how the constraint is different between the different polynomials, right? So we reached the end of the first recap tutorial. Now at the end of each tutorial, we are going to have some recommended videos from across the web that deal with and discuss what we talked about in more depth. So if you want to extend your knowledge, please do. And under the credit sections, you can take a look at further reading, which is relevant to the current tutorial. So thank you for watching, and I will see you next time.